Greetings. Welcome to Electronic Circuits 1. I am Razavi and this is lecture number 27. Today we will look at another amplifier configuration called the the emitter follower, which is realized using bipolar transistors. Before we go there though, let's take a look at what we have learned in the past lecture. So here's where we left off. We looked at the common base topology, and we saw that in that case the input is applied to the emitter and the output is sensed at the collector. That's the definition of the common base stage. And when we calculated the gain, we saw that it is similar to that of the common emitter stage, except that it is positive, not negative. And then we calculated the input impedance, and we saw that it's a relatively low number. And in some applications, that's desirable. And the output impedance was equal to RC, provided that we neglect early effect. Then we looked at the biasing design of the common base stage. We saw that because we need a DC current to flow through the transistor and to ground, we have to have some two-terminal component between the emitter and ground that can carry a DC current. A capacitor cannot do that. So what? Maybe we can use a resistor or an inductor or a current source. So here we have used a simple resistor whose sole job is to allow the bias current of the transistor to go from the positive side of the battery to the negative side of the battery. So what now happens is that RE allows some of the signal current that's coming in to be routed to ground, to be wasted. And to avoid that waste, we would like to maximize RE with some condition like this. Also, we can ask, what is the input impedance of the circuit now that we have RE, in addition to what we had before? Well, we remember that the impedance measured between this point and AC ground is 1 over GM. But now, in addition to that, in parallel to that, we have RE. RE also goes from here to AC ground. So the input impedance of this circuit is now equal to RE in parallel with 1 over GM. So that's also good to remember. This is 1 over GM in parallel with RE. Again, if the early effect is neglected. All right, and then we bias the base using a resistive divider. We chose a collector resistor not to allow the transistor going to the saturation region, and that was the bias design. So today we will repeat some of these procedures that we have followed for the common emitter stage and the common base stage for a third topology. This third topology is called the emitter follower. In some books, in some older literature, we might also call it a common collector topology, but the more common term today is the emitter follower. So let's see what that circuit looks like. So we begin here with the emitter follower, and the circuit is configured as shown here. We have a transistor. The input is applied to the base of the transistor, and the output is sensed at the emitter of the transistor. So here's the output. And this is the transistor, Q1. We have our power supply up here. And this is evidently an emitter follower. Now we'll see why we call it follower, but let's just instantly realize that there is something wrong with the circuit. What's wrong is that we do not have a path between the positive side of the battery and the negative side of the battery for the bias current of Q1 to flow, right? If the current starts from here, positive current starts from here and comes down, it has nowhere to go. So we still need some two-terminal device connected between the emitter and ground. Can I use a short circuit here? No, because if I use a wire to connect this point to ground, then V out vanishes. There's no voltage. So it cannot be a short circuit. So what would I connect? Maybe a resistor, just like the case of the common base circuit. So we connect a resistor here, and we call that RE. Other candidates would be a current source or maybe an inductor, some device that can allow DC current to pass. All right, so this is the emitter follower. What we recognize is that the input is applied to the base, and the output is sensed at the emitter. And that's how we can distinguish an emitter follower from a common base stage or a common emitter stage. As usual, we would like to find the voltage gain of the circuit, and then the input impedance and the output impedance. These are all things that eventually become important when we start building more complex circuits out of these building blocks. All right, so we are interested in AV, R in, and R out. Okay, well, before we go through all of this, and again, for now, we assume that the early voltage is infinite. But before we go through all of this, let's make a qualitative observation that will help us predict some of these things that should come out. So for that, let me change the color of my pen. And let's assume that the device is biased properly, everything is good, we are in forward active region, etc. And I come along and I change this base voltage by some small amount. So I change it by some amount. For example, it goes up. What happens to the emitter voltage? What happens to the output voltage? Well, three possibilities. It stays constant, it goes up, it goes down. Which one do you think is the right answer? Well, this is actually very familiar. If you remember, we did the same test for the common emitter stage with degeneration. The purpose there was something different, but we performed the same test. And we said, well, let's suppose this voltage doesn't change, and the base voltage goes up. Okay, that means that the base emitter voltage goes up, which means the collector current goes up. If the collector current goes up and flows through this resistor, this voltage has to go up. So it contradicts our assumption. So the correct answer is, if the base goes up, the emitter also goes up. In fact, we found an equation to tell us how much of this change goes to the output. That was the gain that we defined from here to here. But for now, that's okay. We don't have to rely on memory too much. But we just do remember that when the input goes up, the output goes up. So for an emitter follower, when the input goes up, the output goes up. We think that the output probably doesn't go up as much as the input. So the gain from here to here is positive. When the input goes up, the output goes up. The gain from here to here is probably less than 1. So that's also good to remember. But we also see why we call this a follower. We see that the output follows the input. Input goes up, the output goes up, and vice versa. All right, so now we can dig into the equations and see exactly what kind of gain we have, and input-output impedance, etc. All right, so let's try to find the voltage gain. So to find the voltage gain, as usual, we go ahead and draw the small signal model. So here's our small signal model, assuming that the output impedance of the transistor is infinite. So we have our pi, then we have V pi, and then we have GM V pi. We have a resistor here, RE. Our input is applied to the base, so that's small signal input V in. The output is sensed at the emitter, so this is V out, which we really mean is the voltage from here to ground. And the collector is grounded because it goes to the power supply doesn't change with time, so its change is 0, so it is grounded. So this is the circuit we want to analyze. Okay, in fact, this analysis is very similar to what we did for the common emitter stage with the generation when we wanted to find out how much of the base change goes to the emitters, right? But again, we'll just try to attack the problem directly here. Okay, well, shouldn't be that hard. Again, we would like to eliminate V pi, and what we recognize is that this current is V out over RE. That's one little factoid to remember. And then we'll, to find V pi, we can just write a KVL around this loop, because we know that this voltage must be equal to this voltage plus this voltage. So that tells us that V pi is equal to V in minus V out. All right, so this V in is equal to V pi plus V out. So V pi must be equal to V in minus V out. Okay, so that wasn't that bad. Now we write a KCL at this node. We know this current, V pi over R pi, and we know V pi. We know this current, GM V pi, and we know this current. So these two have to add up to this one. So we write V pi over R pi. So V in minus V out over R pi plus GM V pi. GM V in minus V out. These must equal to V out over RE. V out over RE. So we bring V out to the other side, factor, etc. You can immediately see that we will have a 1 plus GMR pi here, for example, for V in. 1 plus GMR pi is equal to 1 plus beta. We'll assume 1 plus beta is approximately equal to beta. And then simplify, and this is what we get. We get V out over V in is equal to RE over 1 over GM plus RE. And again, this is the equation we derived before when we were curious to see how a voltage change at the base of a common emitter stage with the generation appeared at the emitter. All right, so it was the same equation, but again, we don't have to remember that. We just see that the voltage gain of a common emitter stage is given by this equation. I'm sorry, the voltage gain of an emitter follower is given by this equation. Now, it's good to, again, to verbalize this result so that we can remember it better. So the voltage gain of an emitter follower is given by, so we say AV is equal to, what do we have in the numerator? In the numerator, we have the total resistance that is tied between the emitter and AC ground, right? From here to AC ground. You can call this RE, call it R5, call it anything you want. That is the resistance. So we say resistance tied between emitter and ground. And by ground, we mean really AC ground, any ground, right? Okay, and in the denominator, we have 1 over GM plus the same resistance. So I'll just put 2 dots here, and then I say plus 1 over GM. So that's what we need to remember for the voltage gain of an emitter follower. Okay. Does this remind you of something, this expression here? Here we go back to basic circuit theory. And I say the gain from here to here is some resistor divided by that resistor plus another resistor. What is that? Well, that's a voltage divider, right? So equivalently, I can think of this as this situation. This resistor has to be RE, and this resistor has to be 1 over GM. We see that the voltage gain from here to here, meaning this voltage divided by this voltage, is RE over RE plus 1 over GM. So we can say that equivalently, an emitter follower does this. If you give it an input voltage, like so, it attenuates it according to this attenuation factor, and it generates a V out here. Right? So this circuit is an extremely simplified version of this circuit or this circuit. Right? Sometimes it's good to remember this. I usually just remember this equation, the way I verbalize it here, because then I can attack any problem that comes my way. But this perspective is also useful in some cases, as we will see later. Okay, so that was the voltage gain of an emitter follower. Now the voltage gain is less than 1. You may ask, what good will it do if the gain of the circuit is less than 1? It seems that a piece of wire is better than the circuit, right? A piece of wire has a gain of 1. Whatever goes in comes out. But this has a gain of less than 1. So why should you use an amplifier with a gain of less than 1? That's something we will study a little later. There is a good reason for it. Okay, then based on this, I wanted to also ask one question before I go over some examples. So let me try to change the color and pose this question to you. Do these results change if we insert a resistor in the collector? And by that I mean take this circuit and insert the resistor here. The output is still down here. But just for the heck of it, I decided to add one more resistor here. Okay, so here's what I'm thinking. I have a circuit like this. The output is still at the emitter because I'm building an emitter follower. The input is still at the base, but I have this extraneous resistor between the collector and VCC. Why did I do that? Well, it doesn't mean that I actually build emitter followers like this, but what happens that in practice, what happens that this may help me with my analysis. It may simplify things, as we will see in a moment. All right, so let's go back to this circuit and see what happens if a collector resistor is inserted here. Does it affect these results? Maybe, maybe not. All right, so if I insert a resistor here, RC, does it affect any of these results? This KVL is still intact. This current is still equal to V out over RE. The KCL here is still the same as before. So whether you have an RC or not, this result doesn't change. With this proviso, you have to make sure that the early effect is neglected. So it is not surprising that this result that we got here was the same as the result that we got before for a common emitter stage with degeneration. Remember, we were curious to see how much of the change from here gets to this point, and we got the result, and the result actually was the same as this. In other words, some of the calculations of the emitter follower are similar to those of the common emitter stage with degeneration. And here's one example. All right, so just keep that in mind, And we'll come back to it in a moment. Okay, so the answer is no, nothing has changed, right, if we insert the resistor. Now let's go over a couple of examples just to warm up with the emitter follower. So here's an example I cooked up. We have an emitter follower receiving an input, and it has a resistor RE to ground. And now I add another stage. I would like to build a two-stage circuit. So I add another stage here, a common emitter stage. These go to VCC, hopefully properly biased. And this is RC, and this is V out, Q1 and Q2. And we'd like to find the total voltage gain of this circuit. So you can see that as we become familiar with more amplifier topologies, we can create all sorts of combinations and permutations, right? Emitter follower with a common emitter stage, or common emitter stage with an emitter follower, etc. So here's one example of that. Okay, so again we have a cascade of two stages. So if I call this node X, I observe that the voltage gain from here to here is equal to that from here to here multiplied by that from here to here. In other words, V out over V in is equal to Vx over V in times V out over Vx. So let's calculate these quickly and then multiply them. Okay, so how much is Vx over V in? Vx over V in is the voltage gain of an emitter follower. Okay, so we go back to this equation here, and we say, we draw a fractional line, and the numerator we have to place the total resistance tied between the emitter and AC ground. So here, from here to ground, I have RE. Do I have anything else? Yes, we also have the resistance that we see between the base and emitter of Q2, and that's R pi, if you remember. The input resistance of a common emitter stage with no degeneration is R pi. So what we really have from X to ground consists of RE in parallel with R pi, and that's what should go up here. And again down here, and to make sure we don't get confused, this is R pi 2, and then plus 1 over GM1 as stipulated by that term over there. So this is the voltage gain from the base of the emitter follower to its emitter, and it's less than 1. Okay. Then we have a gain from here to here, V out over Vx. How much is that? So V out over Vx, well, that's just the gain of a simple common emitter stage with no degeneration. We know that's minus Gm times the total resistance seen between the collector, tied between the collector and the AC ground. So just RC. Again, I'm assuming VA is equal to infinity. So that's just minus Gm2 times RC. That means that the total voltage gain, V out over V in, is the product of these two, right? So we have minus, and we have RE in parallel with R pi 2 multiplied by GM2 times RC divided by RE in parallel with R pi 2 plus 1 over GM1. So that is the voltage gain of the cascade. So again, if we are comfortable and competent with the gains and properties of these stages, then when we encounter a cascade, we don't have to draw the small signal equivalent circuit of the entire thing and try to analyze it. So for this, I need to know the voltage gain of each stage, I need to know the input and output impedances of each stage, and so on. And once I'm comfortable with those, I can quickly write the results. Okay, let's look at another example, again, of mixing and matching different types of stages. So this time I will take an emitter follower. So here's an emitter follower. The input going to the base, the output coming out of the emitter. And now I go to a common base stage. So I need to go to the emitter of the device, then go to a resistor, and then come out. And the base is connected to something, so as usual, we draw a battery here. If you want, we call it V0. And we have a transistor here, Q1, Q2, RC, V out. Sometimes I use lowercase, sometimes uppercase. In small signal models, we always use lowercase to be sure. But for the other general schematic, we can do either one, not a big deal. And then we have a resistor here, RE. So again, we would like to find the voltage gain from here to here, meaning V out over V in. As usual, we call this node X, and we proceed. So this is the quiz of the day. I will give you 90 seconds to write the voltage gain of the circuit. Okay, so what did you get? Well, for Vx over Vin, we have the voltage gain of an emitter follower. We go back to that equation and try to find the total resistance tied between the emitter and AC ground. We have Re here, but how about here? Is there any current flowing through that wire when the signal is applied? If there is, then there's an impedance seen this way to ground as well. Well, we know that the input impedance of a simple common base stage is equal to 1 over Gm. That's what we found last time. And again, that's why we have to be quick with these things, right? So we say conceptually, looking this way, I have 1 over Gm2. That is the input resistance of the common base stage. And 1 over Gm2 means the resistance measured between this point and AC ground. That's our test of input resistance, right? Okay, so we have 1 over Gm2 looking this way, and then we have Re looking down. So we have Re in parallel with 1 over Gm2. That is the total resistance tied between the emitter and ground for the emitter follower. So that tells us that Vx over Vin is equal to Re in parallel with 1 over Gm2 divided by the same resistance. So Re in parallel with 1 over Gm2 plus 1 over Gm of the device, this guy here. So 1 over Gm1. So that's Vx over Vn. And what we need now is the voltage gain from X to V out, so V out over Vx. And we know how much that is. V out over Vx, that's the voltage gain of a simple common base stage. For a common base stage, the gain is positive Gm times the resistance tied between here and AC ground. So again, in all of these, we're assuming that the early voltage is infinite. So we have Gm2 times Rc. And the total voltage gain is just a product of these two. So I'll leave that for you to write. Okay, that was the second example. All right, let's go back to the problem at hand. We managed to find the voltage gain of an emitter follower. We still need to find the input resistance and the output resistance. So one at a time. Let's change the color back to red, and we go and calculate the input resistance, so R in. Okay, R in means what? R in means I sit here and I look this way, meaning I apply a voltage source and I measure the current, and that ratio gives me the input resistance. Of course, everything in small signal analysis. So, all right, so let me do this. Let me draw that circuit again, RE. And my objective is to find the resistance looking this way, right? So if you apply Vx and measure Ix, that's the objective. Okay, now remember what we just said. We said whether we have a resistor in the collector or not, this circuit doesn't feel it. So does it matter if I add a resistor here? No, because you can again think about it this way. I'm interested in this current, right? V in over I in, or Vx over Ix would be the input resistance. Now, does this current get affected whether we have RC here or not? No, because none of the equations that we wrote here changes, right? So I in doesn't change, V in over I in, or Vx over Ix doesn't change. Okay, so do I know something about this circuit, this input resistance, without without drawing an equivalent circuit? Yes, because this circuit looks like a common emitter stage with degeneration. And we already have the input impedance of such a stage. So what we know is that R in is equal to R pi plus beta plus 1 times RE, because we said the transistor takes the emitter resistor and boosts it up by a factor of beta plus 1 before placing it in series with R pi. So that's what it is. We don't have to solve the circuit. We don't have to solve this circuit or that circuit. So this brings up a very important point. When we are calculating the input resistance of a circuit, we don't know where its output is. I repeat, when we are calculating the input resistance of a circuit, we don't know where the output is. If the output is here, that becomes an emitter follower. If the output is here, that becomes a common emitter stage with degeneration. But as far as the input resistance is concerned, we don't know where the output is, and we don't care. So this result applies to both an emitter follower or a common emitter stage with degeneration. It's the same thing. All right? In this result also, we're assuming that the early voltage is infinity. Okay, so remember that. Very good. Now, if you're not happy with this interpretation, you can just find V in over I in the circuit and simplify it, and you'll get the same result. So that's not a big deal. All right, one last item is R out. So let's try to find R out. R out means the output resistance of this circuit. Now we have a procedure for that. We say set all independent sources to 0. So this guy has to go to 0. This guy has to go to 0. place this in a box, and apply a voltage from outside, Vx, find the current Ix. That ratio gives us the output resistance. This is similar to finding the Thevenin equivalent of the circuit. Okay, so certainly we can do that, not a big deal. I can sit here and do that calculation, right? I can set this to 0 and so forth. So let's do that, but with a slight modification. So I will draw the small signal model of the transistor knowing that Vin has to be 0 for output resistance calculation. So let's do that. Here's our, sorry, let me do this. All right, so we set our input to 0. All independent sources have to be set to 0. We have R pi here. Then we have V pi. Then we have GM V pi. The collector goes to ground. And now we have a resistor from emitter to ground, right? Okay, I will draw that a little to the right, just for a reason. So I draw it here. I hope you agree with me that doesn't do anything. Let's see, my pen has frozen. Let me take the other pen and see, maybe this pen is better. Okay, so we have R pi, GMV pi, and now let's go back to red. Okay. All right, so I will draw RE over here. RE. That's okay, right? So far I haven't done anything illegal. And now I go ahead and apply Vx and measure Ix. So I have to apply Vx here. And measure Ix here. Right? We said we put the whole circuit in a black box, and we go to the port of interest, we apply voltage, measure the current. All right, no problem. So that's what we have. Okay, and remember that RE is connected to ground. Okay, so what can I observe before I jump into the equations? Well, RE goes from emitter to ground. In other words, RE is exactly in parallel with Vx. So because Vx is trying to find the resistance from here to ground, and we already have RE from here to ground, we can take RE out for now, calculate everything else, and then take the result and place RE in parallel with it. Right? Because whatever we're calculating from here is still with respect to ground. And if we take RE out and place it back in, the result will be the total output impedance. So I will gently cross this resistor out. But you remember that it's there, okay? It's there, and it's simply in parallel with the voltage source. So if you don't want to do it this way, you can just draw it on this side for now, right? And we'll try to find the resistance of the rest of the circuit. Okay, in fact, I can do it this way so that you remember it's still there, RE. All right, I moved it from the left to the right. The topology hasn't changed. And what I will do is find the resistance that I see looking this way. That's a resistance to ground. And then I remember that, there's one more resistor to ground, RE, and they're in parallel. Okay, so let's go find the resistance of this topology here. Okay, how much is that? Well, we just write the KCL. We have V pi over R pi plus GMV pi is equal to minus Ix, or the three add up to 0. And we also notice that Vx and V pi are related. they're both in parallel with R pi, except that V pi is flipped, so V pi is equal to minus Vx. V pi is equal to minus Vx. So then, if I write a KCL, I have minus Vx over R pi minus GM Vx equals Ix. And again, remember, this Ix is calculated without the resistor Re considered yet. Okay, so what happens? I can factor, minus V or plus Ix equals 0. That's better. I can factor Vx out of here, or minus Vx. So what I see is Gm plus 1 over R pi. So how does Gm compare with 1 over R pi? Well, we know that Gm times R pi is beta. So Gm is much greater than 1 over R pi. Right? So Gm is much greater than 1 over R pi. We can neglect this term, keep that term. In a sense, we are neglecting the base current compared to the collector current, right? V pi over R pi versus Gm R pi. Gm V pi. Okay. So that tells us that Vx over Ix is approximately equal to 1 over Gm. All right, so let's see what we have accomplished so far. What we have discovered is that the impedance seen by Vx, if we exclude Re, is equal to 1 over Gm, if it looks this way. And that means the impedance seen between this node and AC ground, because Vx is connected between this node and AC ground. But we remember that there's another Re in there, and that Re goes from the same node to ground, so the total output resistance of the emitter follower is equal to Re in parallel with 1 over Gm. So I don't want to go to another page. I want you to have all of this on one page. So I will write R out as 1 over Gm in parallel with Re. Okay, that is the output resistance of the emitter follower. So why did I do this? Why did I take Re out first? Well, I want you to become comfortable looking at the circuit and deciding which simplifications can be made before you jump into the equations. We can now readily see that this output resistance consists of two parallel components. If we had not recognized that at the beginning and kept Re and written all the equations, you would end up with something more complex that might not have the intuition that we have here. Okay, very good. So we have found the input resistance, the output resistance, and the voltage gain of the circuit. Does this output resistance look familiar? Yes, it looks familiar, and it looks strange. Strange and strange. Okay, so where is this? This is the resistance that we see here. If we sit at the emitter and measure the resistance, of course with the input source set to 0, we measure 1 over Gm in parallel with Re. 1 over Gm in parallel with Re. 1 over Gm. What is 1 over Gm? 1 over Gm is the impedance seen at the emitter, and Re is down here. So this is beginning to look familiar because it's actually similar to this equation here. So let me try to put both of these next to each other, and you can see both of them. So this equation is 1 over Gm in parallel with Re. What is this? This is the impedance seen at the input of a common base stage with Re connected from here to ground for bias calculations, and then 1 over Gm, right? This is what we had here. Now, why should this look the same as the output impedance of the emitter follower? Well, Because remember we said having an RC here or not doesn't make any difference, right? So whether we have this circuit as a common base stage and we are sitting here and looking into the emitter, or whether we have this circuit and looking into the emitter, we should see the same thing, because this resistor doesn't play a role in what the circuit does, as long as early effect is neglected. So that's also interesting. That points to yet another important fact. If we are interested in the output resistance of a circuit, we don't know where the input is. In fact, sometimes we don't even know whether this is an output node or an input node. And that's perfectly fine. So long as we do the calculations correctly, we set all the independent sources to 0, and we find the impedance between two nodes, that impedance is some amount. And it doesn't matter whether you want to call it an output impedance or an input impedance. The only golden rule is to set all independent sources to 0 when we are calculating the impedance between two nodes. All right, and that's why these two happen to be the same. Okay, very well. Let's go on to another example just to get comfortable with these things. So what I want you to remember are, number one, the input impedance of the emitter follower is R pi plus beta plus 1 RE. And the output impedance is 1 over GM in parallel with RE. Okay. All right. Now let's go and look at another example. So I will insert a new page here. Here's an example. I take an emitter follower like before, and I have a resistor here. But I just happen to have a resistor in series with the base of the device, like so. Okay, and then the input is here. So maybe we'll draw a voltage source. You don't have to draw a voltage source, but anyway, I drew it. V in, and the output is here, V out. Now, that resistor RB is not deliberately introduced in the circuit because that only degrades things, as we will see. It reduces the gain and everything else. But sometimes RB represents the output impedance of the circuit before this circuit. Okay, this seems a little unfamiliar to you, but don't worry about it. I just want to tell you that RB is not something that you deliberately add to your circuit to an emitter follower. Okay, so we would like to find the voltage gain, the input impedance, the output impedance, and all the good stuff. All right, so how do we do that? Well, you can always draw the equivalent circuit, but again, we want to resist that temptation. We want to look at the circuit for a little while and see if our previous results can be used to find, for example, the gain by inspection. All right, well, why don't I do this? Can I call this node X? And as usual, I say the total gain is Vx over V in times V out over Vx, right? Let's do that. So how much is Vx over V in? Well, we can sort of see a voltage divider, right? A resistive divider. We have a divider consisting of this resistance and then some resistance from X to ground. If I can replace this entire circuit with one resistance to ground, then I have a simple voltage divider. So how much is the resistance that this circuit presents at this point? That would be the input impedance of the circuit. So I put an arrow here, and I say the input resistance of an emitter follower is R pi plus beta plus 1 times RE. It takes this and boosts it up by this factor and then places it in series with R pi. In other words, this circuit simplifies to RB a nice little voltage source here, V in, and then this resistance here. And this is node X. Right? As far as the signal propagation from here to here is concerned, we can have this equivalent circuit. So Vx over Vn is just that of a divider. So it would be this resistance divided by the sum of the two. R pi plus beta plus 1 times Re divided by the same resistance plus Rb. So R pi plus beta plus 1 times Re plus Rb. That's the voltage gain from V in to Vx. It's really an attenuation, but you can call it a gain too. The next step, we find the voltage gain from X to V out. So V out over Vx. How much is that? We know that already. That is the voltage gain of an emitter follower. So the gain of an emitter follower is given by the total resistance tied between the emitter and ground, Re, divided by Re plus 1 over Gm. So the total voltage gain is just the product of these two. So we say V out over V in is that times this. Now let's manipulate the results because something interesting may come out. We have R pi plus beta plus 1 over Re. I will factor out beta plus 1. And I remember that R pi over beta plus 1, or R pi over beta, is approximately equal to 1 over Gm, right? So this is what we have. If I factor this out, I have 1 over Gm plus Re, 1 over Gm plus Re, and then here I have 1 over Gm plus Re plus Rb over beta plus 1. I am factoring beta plus 1 out from the numerator and the denominator. So 1 over Gm plus Re plus Rb over beta plus 1. And then we have V out over Vx, so that's just Re over Re plus 1 over Gm. Interestingly, this denominator and this numerator cross, so we end up with this nice little equation for the voltage gain of this particular emitter follower. 1 over Gm plus Re plus Rb over beta plus 1. Okay, so that's the voltage gain of this emitter follower. When we have a resistance in the base, for any reason, it manifests itself in the voltage gain with this factor of Rb over beta plus 1. Okay, we also need to find the input resistance. Input resistance meaning from here, that's the input of the box. That's not that hard. That's just this Rb plus this guy, right? But plus whatever we had here. So that's not that hard. R in is equal to Rb plus R pi plus beta plus 1 times Re. Visit here, we have Rb and then we have the rest of the stuff, right? So they add up. Okay. Now let's go on to R out. R out is the output resistance of the circuit. Meaning I sit here, I set all independent sources to 0. This is 0, that's 0. I apply a Vx here, measure Ix, and that ratio is the output resistance. So is this something that I am already familiar with? Not really. We don't have any circuit that looks like that. We really never placed a resistance in series with the base of a device, right? Okay, so then how do we do that? Well, I will play a little trick here, okay? Of course, you can draw the small signal model and calculate and see what comes out. But because I'm lazy, I will take a shortcut. So here's what we're going to do. Let's change the color of our pen to something more exciting. All right, so for R out, I look at this voltage gain expression very carefully, and I see something familiar. We have a resistor divided by that resistor plus some other things. Is that familiar? Yes, that is the expression for a voltage divider. So let's construct that voltage divider. This is what we have. So we're not at R out yet. We're just manipulating this, right? So if I'm manipulating this, I'm saying that what the circuit does, this whole circuit, is it takes the input, this input, and it subjects it to an attenuation, a resistive attenuation, where we have RE here, because it appears in both the numerator and the denominator. And then the rest would be this resistance. So let me clean this up. So the rest would be 1 over Gm plus Rb over beta plus 1. And this is V out. Is that correct? This is an attenuator, right? A voltage divider whose gain or loss is equal to Re divided by Re plus this. So that's that. So equivalently, we can view the operation of the circuit as the operation of a voltage divider. Okay. So far so good, right? Now, so for all practical purposes, I can say that this circuit represents this circuit. Do you agree with that? So if it does, then I can say, instead of finding the output resistance of this circuit, I will find the output resistance of this circuit. And to find the output resistance of this circuit, I have to set the independent source to 0. So for R out, I will do this. I will set the input source to 0, 1 over Gm plus Rb over beta plus 1, and then Re. And then this is V out. Sorry, this is what we are trying to find. So that's the output resistance. So we're trying to find the output resistance here. And now it's clear what it is. The output resistance is equal to Re from here to ground in parallel with this. So we see that it's equal to Re in parallel with 1 over Gm plus beta plus 1 sorry, let me clean this here, go back here, plus Rb over beta plus 1. This is a fascinating result because it is somewhat similar to the output resistance that we found earlier for an emitter follower when Rb was not there, when Rb was 0. So if Rb is 0, what do we have? We have Re in parallel with 1 over Gm, and that's what we had before. That's what we calculated. But now that we have a base resistance, the output resistance, meaning if I sit here and I measure the output resistance, is not just Re in parallel with 1 over Gm. What the circuit does is it takes the base resistance and transforms it down, reduces it by a factor of beta plus 1, and then adds it to 1 over Gm. Okay, and then it goes in parallel with Re. So that's the only difference between when we have a base resistance and we don't have a base resistance. So again, I like this approach because it readily shows what's going on in the circuit. Otherwise, if I draw the small signal model and do the calculations, I end up with some big expression and I have no idea what is what. So that's the output resistance of that circuit. Okay, All right. Our time is up. Next time we will take another look at the emitter follower, some of its other properties and its bias conditions, and then we move on to other interesting circuits. I will see you next time.